Hi everybody, I hope this video finds you well. In this video, we're going to be working our way through section 3.3 from your textbook, which is the last section required for exam 2. So in this section, we're basically going to learn an alternate computational mechanism for calculating determinants that can be sometimes pretty useful, and we're also going to introduce a very important definition that, while maybe not super important right now, is something we're going to revisit a tremendous amount in a couple weeks. So we're going to get that definition sort of stated and look at a couple examples of it. So the first definition, though, that we need to talk about to set up this alternate way of calculating determinants is what's called the minor of a matrix. So the minor is defined as follows. So we've got A is an n by n matrix. Then the minor of the ijth element, and it's denoted m sub ij, is the determinant of the n minus 1 by n minus 1 matrix formed by deleting row I and column j from A. So in other words, the minor of an element is the determinant of the sort of one size smaller square matrix formed by removing the row and column of that ijth element. So you can sort of think about the minor as the determinant of a one size smaller square matrix. So as a quick example, to just make sure you guys are comfortable with this definition, let's go ahead and write down but not evaluate expressions for these minors here. So let's look at M11. So in that, we'd want to talk about the determinant that would result from removing the first row and first column. So we'd be thinking about removing first row and first column. So we'd have this determinant here. So this guy would be equal to the determinant of 5. Let's do that in our normal color there. M11 would be the determinant of 5, 2, minus 1, 3, 8, negative 6, 1, 2, negative 5. And again, we're getting that by simply deleting the first row and first column because we're talking about M11. Notice that this, because it would be a determinant, would just be a number, right? It's not a matrix, it's the determinant of a matrix. So a minor is just a value here. All right, if we talked about M23, well, M23 would be deleting the second row and third column. So we'd have those remaining elements. So M23 would be equal to 2, 0. We said we're deleting that guy in there. So it looks like 2, 0, 4. And then we said this guy and this guy. So 0, 3, 1, 7 down there. 0, 3, 7, 1. And then we cross up this guy and this guy, negative 6 and negative 5. So it would be the determinant of that matrix. Notice that each of these is a 3 by 3 matrix because A was initially a 4 by 4 matrix, and the minor is always the determinant of a one size smaller square matrix. So that's what the minor of a particular element is. Why do we want this definition of the minor? Well, it turns out that we can use this definition of the minor for a very direct computational way of calculating the determinant of a matrix. So this is what's called the cofactor expansion of a matrix. So we'll state this as a theorem here. So the cofactor expansion theorem, you can expand along a row or along a column. You choose one of the two, and then you can calculate the determinant. So if you decide to expand along row I, what you do to calculate the determinant is you take the first value in that row, ai1, you multiply it by minus 1 times I plus 1. You can think about that I plus 1 as the position. And then you multiply that with the minor that comes from taking of this element, so mi1. And you do that for all the values in that row. So ai2, and then all the way down to ain, because we're expanding along row I. You can do this also using the column j. So there you would start with a1j, minus 1 to the I plus j, and then the minor for that aij element. And you would do that for every element in the column of j, so a2j all the way down to anj. So what does this cofactor expansion theorem really do? What it does is it tells you how to take the determinant of an n by n matrix, A, in terms of n minus 1 by n minus 1 matrices. Then you could apply this cofactor expansion theorem to each of these minors and think about those in terms of n minus 2 sized matrices, and so on and so forth. So this cofactor expansion theorem basically gives you an iterative process for reducing the size of the matrix so that you can find the determinant. Is this a particularly computationally efficient method? Not really. It can get pretty computationally intensive, but it is better than just using the straight definition. So we're going to do a couple examples with this, and then we'll also see how this can be combined with some of the previous methods you learned, namely the use of elementary row operations. So first, though, just to get a sense of this cofactor expansion theorem, what we're going to do is we're going to take this matrix A here, and we're going to write out, but we're not going to take the time to actually evaluate it just yet because this one would be pretty messy, an expression for the determinant of A using the cofactor expansion along the first row. So in this case, what we would say is we'd say, okay, determinant of A, we'd start by taking the first value in the first row. So we take that 2. So we do 2 times, and then we do minus 1 to the position. And since this guy was in first row, first column, that would be to the 1 plus 1. And then we would multiply by the minor for that element, which would be the determinant, crossing those out, of this 3 by 3. So it would be the determinant of 5, 2 minus 1, 3, 8 minus 6, 1, 2 minus 5. Then we would continue along the row and we'd go to this guy. So we do plus 0 times his position. He's in the 1, 2 position, so minus 1 to the 1 plus 2. And then his minor, which would be crossing that out and crossing that out. So you would have minus 1, 0, 7, 2, 8, 2, minus 1, minus 6, minus 5. Now, if we were actually computing this, would we bother with this one? Well, no, because that 0 there would make this entire term 0, which sort of gives you guys a hint that a efficient use of this cofactor expansion is if you can cofactor expand along a row or column that has lots of zeros. But for now, let's continue on. So we would move to the next one, which would be this element 3, since we're going along the first row. 3 times minus 1 to its position. This is row 1, column 3, so 1 plus 3. And then we would take that out and that out. So it looks like we'd have minus 1, 5, 0, 3, 7, 1. And then we took this and this out, so we also have minus 1, minus 6, minus 5. And then finally, we'd add one more thing, which would be this last guy here. So 4 times that position, which would be, he's in the 1, 4 position, so 1 plus 4. And then we'd be taking this minor, so we'd cross all that stuff out. Minus 1, 5, minus 1, 5, 2, 0, 3, 8, and 7, 1, 2. And if you then went through and evaluated these determinants, right, then that would give you the determinant of A. How could you evaluate these determinants? Well, you could then take these guys and cofactor expand these into size 2 determinants, so on and so forth. But this is what the cofactor expansion is. If we choose to cofactor expansion along a different row or a different column, you will get a different set of values. But of course, it will sum up to the exact same determinant because the determinant is just the determinant. All right, so this gives you guys hopefully a sense of what the cofactor expansion looks like. In terms of proving the cofactor expansion theorem, your book does a proof of it. It's pretty messy. I don't think it's the most important thing. To be honest, for our class, cofactor expansion can sometimes be useful in small cases like 2x2s and 3x3s. Anything larger than that, we generally favor elementary row operations. So we're not going to take the time to go ahead and prove this expansion theorem. If you want to see the proof, there is one in your textbook though. Instead, let's just do a couple examples to sort of get used to what this is really saying here. So let's go ahead and actually calculate a determinant using this. So a quick useful note that you've probably seen if you've looked through the textbook already is that 2x2 matrices have a very clean just formula for determinants. If you ever have a 2x2 matrix, the determinant is A11 times A22, which are the diagonal elements. minus the product of the off-diagonal elements, A12, A21. So this is a very quick formula that you should pretty much always have at the ready. And this sort of tells you with cofactor expansion, if you can reduce things to 2 by 2 determinants, you can then use this formula to fill in those determinants. And that's what we'll attempt to do on this guy. So for this guy here, we're going to try to calculate the determinant of B. Now we could cofactor expand along any row or column, but it would probably be nice to use the one that includes that 0 there. So we could cofactor expand along row 2 or column 2. It doesn't matter. Since we did a row expansion as our first example, let's go ahead and expand along column 2. So let's expand via column 2. So we would say that the determinant of B then is going to be this element, so 4 times minus 1 to the position. That guy is in the 1, 2 position, so 1 plus 2, times the corresponding determinant when we use that minor. So we'll close that up, and we'll get minus 1, 5, 1, 8. Then we will add to that, well, we don't even need to worry about the next one because the next one will be 0. So we can just say plus 0. And then plus this guy down here, so that'll be 6 times his position, which is minus 1. He is in the 3, 2 position, so 3 plus 2. And then the minor for that would be crossing that out and that out. So it looks like we'd get 3 minus 1 and 2, 5. Okay. We could, of course, cofactor expand these, but we have this nice little expression for the determinant of those. So we can say that the determinant of B here is going to be, that's going to be negative 4. Then this, we can do this as negative 8 minus 5. And then plus, well, it looks like it'll actually come out as minus over here because this is going to be 6 times minus 1. So that's going to be minus 6 times. Then, according to this here, we multiply these two together. So we get 15. And then we subtract this product. So that's going to be plus 2. Okay, so let's go ahead and then do that, right? So now it's just arithmetic. That tells us that the determinant of B here, that looks like what? Negative 13 times negative 4. So that's going to be 52. And then this is going to be 17 times 6. So what is that? That's going to be 60 and 102, I think. Let's make sure. 17 times 6. Yeah, 102. So minus 102. So that tells us that the determinant of B is equal to negative 50. Notice if we were curious, that also tells us some other things. That tells us B actually does have an inverse. It also tells us that the rank of B is 3, because if you have an inverse, then you have full rank. And since this guy is non-zero, we know it does have an inverse. We also know its rank is full. But that would be its determinant. If you wanted to use elementary row operations, you could certainly do that too. Wouldn't be too hard to maybe move this guy up to the top, use that as a pivot, clear out the stuff below it, and then go from there trying for upper triangular, and you will of course get the same thing as you did in this case. All right, so that's our first example of using cofactor expansion. Now, in the next example, we're going to sort of use cofactor expansion along with some elementary row operations. So let's go ahead and take a look at that. So in this guy, we have this sort of very large 4x4 matrix, which could be very tedious to sort of calculate directly. Now, we could try to use elementary row operations the entire way and, you get it into upper triangular form. But let's be sort of smarter. Remember, a lot of these things are algorithms that are really good for computers, but we can do a bit better if we can sort of detect or spot really clever uses. Notice we can use an elementary row operation to get a ton of zeros right away. If we take row 1 away from row 2, we will get an almost row of zeros. This guy won't be 0, but everything else will actually be 0. So let's do that first. So if we're trying to calculate the determinant of C, we can say that that's the determinant of 3211, 3215, 5704, 0120. So let's do an elementary row operation, and let's do row 2 and replace it with row 2 minus row 1. Now remember, this third type of elementary row operation doesn't change the determinant. So this actually will be equal, right, in terms of determinant here. So we get 3, 2, 1, 1, and then we get 0, 0, 0, 4. And then 5, 7, 0, 4, and then 0, 1, 2, 0. Okay, now we could even get more zeros. You know, we could use this guy now to clear out the 4 right there. But let's just go straight from here. Let's immediately cofactor expand along row 2. So now let's do a cofactor expand via row 2. So, of course, all of these won't contribute anything. We'll only have to worry about that. So we will get then that that is going to be 4 times minus 1 to this position. This guy is in the 2, 4 position, so it's going to be 2 plus 4. And then the minor that's associated by crossing that out and crossing that out, looks like we get 3, 2, 1, and then 5, 7, 0, and then 0, 1, 2. And if we wanted to simplify a little bit, that looks like, because that's going to be a 6, this is going to be positive. So it looks like we get 4 times the determinant 3, 2, 1, 5, 7, 0, 0, 1, 2. And now we need to deal with this guy. So this is a 3 by 3, so we can cofactor expand again. Might be good to cofactor expand along row 3 or column 3 or row 2, any of those ones that include a 0. So just for fun, let's cofactor expand via column 3, just to get more practice doing it. So we'll have our 4 outside, and then we're going to cofactor expand along here. So we'll take our 1, then minus 1. That 1 is in the 1, 3 position, so 1 plus 3, times the corresponding minor. So that's going to be 5, 7, 0, 1. And then we're going to add to that. We won't have to worry about this guy, so we'll just go right to this one. 2, his position is minus 1 to the 3 plus 3. And his minor there is at 3, 2, 5, 7. So 3, 2, 5, 7. All right. Now for each of these, we got 4. This is going to be positive 1, so we don't really need that. And we can do that cross and then minus that cross there. So that looks like that's going to come out as 5. And then this guy here, this is also going to be positive. So we're going to get plus 2 times this cross minus this cross. So that's 21 minus 10. So that's going to be an 11 there. So it looks like that's going to be 22 and 27. And looks like we're going to get 108. So the determinant of C here is 108. That tells us that C is invertible. It will have an inverse. And it would also tell us that the rank of C is going to be 4, because again, to have an inverse, you have to have full rank. So this shows you guys one that would have been pretty messy to do most other ways. But by using a sort of smart combination of an elementary row operation, specifically using one that doesn't sort of change the determinant, those ones are really useful when you plan on still cofactoring, expanding, so you don't have to also keep track of any like negative signs or scalar multiples. Then if you can build a lot of zeros, this cofactor expansion is very quick. So this is a sort of good strategy, right? My general recommendation is if you need to calculate the determinant of a large matrix, use a couple of these sort of third type of row operations to clear out and get as many zeros as possible, and then just start to cofactor expand. All right, now to wrap this up and to give ourselves a couple more examples to work on, we're going to define a very important thing, a property of a matrix that we will explore a lot more later on, especially when we start to tie all this stuff into differential equations. But we're going to define it now and look at a couple examples. So this is what's called an eigenvalue of a matrix. So an eigenvalue is just a value, as you would expect. We usually use the sort of symbol lambda. So an eigenvalue of a square matrix is just a value or a scalar that causes this to occur. It causes the determinant of A minus lambda in. So A minus lambda times the identity matrix to have a determinant which is 0. So let's see if we can use this definition to find the eigenvalues of this matrix. So how do we do that? Well, to find the eigenvalues of this matrix D here, what we first need to do is we need to consider D minus lambda I. which if you think about it would be 2, 4, 3, 1 minus lambda 0, 0, lambda. And if you think about what that matrix looks like, that's 2 minus lambda, 4, 3, 1 minus lambda. Notice what that basically did is when you subtract lambda I, or a minus lambda in in this more general definition, that's just taking lambdas and subtracting them from the diagonal. Now we need the determinant of this, of 2 minus lambda, 4, 3, 1 minus lambda, to be equal to 0. Now this over here is a determinant, so this actually comes out as a value, and we have it set equal to 0, so we can get an equation to solve. Now this is 2 by 2, so we know that we can do this the quick way, so with this cross minus this cross. So we get 2 minus lambda, 1 minus lambda, minus 3 times 4 equals 0. Now we're in a very sort of safe place. We just got some multiplication, some FOIL here. Lambda squared minus 3 lambda plus 2 minus 12 equals 0. That looks like lambda squared minus 3 lambda minus 10 equals 0. And that sounds like lambda minus 5 lambda plus 2 equals 0. And that gives us that lambda equals 5 and lambda equals negative 2. So lambda equals 5 and lambda equals negative 2. Those are the eigenvalues of this matrix. If you check, if you subtract 5 off the diagonal, or you subtract negative 2 off the diagonal, you will get a matrix that does have a determinant of 0. Let's see if we can just see that in our heads. If we subtract 5, notice that if you subtract 5 off the diagonal, you'll get minus 3, 4, and then you'll get 3 minus 4. But if you think about that, this row here would just be a scalar multiple of this guy. And we know that anytime one row is a scalar multiple of another row, the determinant is 0, and that shows you we satisfied that definition. Eigenvalues are an incredibly important property of matrices, and they're going to be very, very useful when we start to tie this into solving systems of differential equations. So getting used to calculating the eigenvalues of a matrix is something we're going to do a lot of. Let's look at one more example to also get some practice with the cofactor expansion. So we've got this matrix here. We'd like to find the eigenvalues. So we first consider E minus lambda I, which of course is going to be the matrix minus lambda, 1, 2, 0, 3 minus lambda, 3, 0, 2, 3 minus lambda. Okay, so we've got that guy there. That's going to be our matrix. Then we need to go ahead and calculate the determinant. So we're going to take the determinant of minus lambda, 1, 2, 0, 3 minus lambda, 3, 0, 2, 3 minus lambda, and we're going to set that equal to 0. How are we going to evaluate this determinant? Well, easiest way would be to cofactor expand along column 1. So that would be minus lambda times minus 1 to the position there, which is in the 1, 1, so 1 plus 1. Then times the minor, which would be this, and we'd get 3 minus lambda, 3, 2, 3 minus lambda. And that would be equal to 0. And of course, the other ones wouldn't contribute anything because they have an element of 0. We can simplify that a little bit. That would be minus lambda, because the minus 1 to the 1 plus 1 isn't going to matter. And then, of course, this is a 2 by 2, so we can just do this minus this. So this would then become, I'll use some brackets, 3 minus lambda times 3 minus lambda minus 2 times 3. And that would be minus lambda. And I'll continue the brackets there. Looks like that's lambda squared minus 6 lambda plus 9 minus 6. Something like that. Although I'm fearing now that I made a mistake. Did I make a mistake here? You can hear my dog sigh in the background. Well, no, I guess this one will just be a little bit messy. That's okay, though. So this will equal 0 here. And we'll get minus lambda. Lambda squared minus 6 lambda. Plus 3 equals 0. Okay. Just making sure, I intended this guy to be a little bit cleaner than that, but that's okay. So now we would just need to solve this, right? This part is easy. That's going to contribute a lambda equals 0. So we get lambda equals 0 is one eigenvalue, and then we get lambda squared minus 6 lambda plus 3 equals 0. This will be a little bit messier. We'd have to use like a quadratic, the quadratic formula, but that's not too bad. 6 plus or minus the square root, 36 minus 12 over 2. And it looks like that would be 6 plus or minus root 24 over 2, which looks like we'd get lambda is 3 plus or minus root 6. So we would have 3 eigenvalues for this matrix. Lambda equals 0, and then lambda equals 3 plus or minus root 6. So those are all things that if you subtracted them off the diagonal would give us a determinant of 0. So again, eigenvalues, we might not know quite why they're so important right now, but they are going to be something we use quite a bit of. So right now, it's mostly just to give you guys some more practice using cofactor expansions, but not always just calculating a direct determinant, now using the determinant to set up an equation that we then want to be able to solve. All right, so the last thing that we'll go ahead and take a look at here is just a quick proof, just to give you guys some more practice with that sort of thing that involves this eigenvalue concept. So let's move on to our last piece in here. So we're going to try to prove this. We're going to prove that if lambda is an eigenvalue of matrix A, then lambda squared is an eigenvalue of matrix A squared. So let's think about how we would do this. So we get to assume that lambda is eigenvalue of A. So what do we know that means? That means determinant A minus lambda in equals 0. So we get to assume that. And what do we need to show? We need to show lambda squared is an eigenvalue of A squared. So we need to show that the determinant of A squared minus lambda squared in equals 0. So this is what we need to show. So let's think about how we can work with this. One way, of course, to attempt the proof is to pick one side of your need to show and show how you can work to the other. So let's attempt to do this. Our proof here, we've got the determinant of A squared minus lambda squared in. Well, this should sort of look a little suspicious to you guys. This is like an A squared minus another square. So let's see if we can break that up, right? We can sort of think about that as the determinant of A minus lambda in times A plus lambda in. Now let's see if we are convinced by that. Well, if we sort of imagine foiling this out, A and A is going to make that A squared. A and in is just going to make an A. So we're going to get, when we bring this in, we're going to get a lambda in, or a lambda A. But we're going to get a minus lambda A when we do those two. And then, of course, when we multiply these, we get minus lambda and lambda. That would make lambda squared. And we get in squared. But the identity times the identity, still going to be the identity. So this is definitely true here. Now, what do we know about determinants of products? Well, in the last video, we saw that the determinant of a product is the product of the determinants. So we could break this up as the determinant A minus lambda in times the determinant A plus lambda in. All right, but do we know anything about these? Well, by assumption, we know that the determinant of A minus lambda in is 0 because lambda is assumed to be an eigenvalue. So we know that this is 0 times the determinant of A plus lambda in. Now, we don't know anything about this, but 0 times anything, well, that's just going to be 0. And we did it. That shows that lambda squared is an eigenvalue of A squared. So this shows you guys that if you know an eigenvalue of a matrix A, then that square of that eigenvalue is guaranteed to be an eigenvalue of the square of that matrix. So I know eigenvalues might seem a little weird, and again, we haven't really seen why they're going to be useful, but we just wanted you guys to get a little practice with this definition. Also just sort of useful, again, still manipulating properties. We got to use that sort of nice property that the The determinant of a product is the product of the determinants. So again, just trying to give you guys some additional practice with that. If you look in your textbook for section 3.3, there are 2 topics in 3.3 that we are not covering. There's a discussion of the adjoint method for finding the inverse. We're not going to be discussing that in our class. You're welcome to read it and use it if you want to, but it is not something we will be covering, and I don't really recommend it as a technique. And there is also something called Cramer's rule, which is a way of using determinants to solve systems of linear equations. It is a really great approach for computers to use because determinants are something that they can be programmed to calculate very easily. But for humans, Cramer's rule is not a particularly great way of solving systems. So we're not going to really talk about it in our class. Once again, though, you're welcome to take a look at it if you're interested. Otherwise, this wraps up chapter 3 for us and all the sort of material that you guys need for your second exam.